Hello stormwater designers, welcome back to Clear Creek Solutions hydrology education videos. And in this one in the series, it's Hydrology 101 again, and we're going over hydrograph analysis. You can pick up our free hydrology terms guide if you go to the description down below. It's 3 to 4 pages of defined hydrology and hydraulic terms that is really useful for reference, no matter what stage of your education or your designs you are. So you can pick that up in the description down below. Now let's get into hydrograph analysis. So remember we talked about interflow, groundwater flow, surface flow in the last lesson. So we're talking about how that relates to hydrographs here. So the characteristics of direct and groundwater runoff differ so greatly that they must be treated separately in problems involving short-term or storm runoff. So when we have a specific storm event, groundwater is going to lag significantly behind your storm event and maybe even the result of previous storm events. So we have to find a way to separate that groundwater from the more surface and interflow runoff that we're going to get from a short-term storm event. There's no practical means of differentiating between groundwater flow and direct runoff after they have been intermixed in the stream. So it's actually difficult to differentiate this. We have to look at hydrographs and other data to decide where we think the groundwater flow is that is constant and use that to separate it from the rest of the runoff that occurred from the stormwater event. The typical hydrograph resulting from a single storm consists of a rising limb, peak, and recession, and we'll take a look at a few graphs here shortly. The recession represents the withdrawal of water stored in the stream channel during the period of rise. And then double peaks are sometimes caused by the geography of the basin, but more often result from 2 or more periods of rainfall separated by a period of little or no rain. So if you view the hydrograph and it has a double peak, it could be the geography of the region. Most likely it's just 2 concurrent stormwater events with a little bit of separation. And numerous methods of hydrograph separation have been used to identify these different components. So here's our first hydrograph example here. We have the peak precipitation, we have that rising limb, and then we have the recession. And then we can see the blue area is the storm flow. And you'll notice that in most cases, we want to separate this base flow / groundwater flow from the hydrograph. We can see that that's the yellow portion there because it doesn't really fluctuate a whole lot based off the storm event. There's a small rise there at the end of the storm event, but it's mostly occurring just as the general base flow of the stream or could come from previous storm events. So this is a good example here of what a hydrograph could look like over 4 days of a specific rainfall event here. Then here we can see the effect of urbanization or the use of impervious area on a hydrograph there. So we can see that the peak discharge coming off the recession is much greater after urbanization than before. Because think about this, if we have impervious area, the water is not going to infiltrate through the soil or through the surface because it's impervious during an urbanization development. And so we're going to have more discharge coming off the area because of that. And then we're going to have even less discharge before that. And so that's one of the bases for a lot of the hydrology software that Clear Creek Solutions creates. We're trying to match and prevent the erosive flows that comes from urbanization. And so we're trying to match the pre-developed and mitigated flows to prevent those erosive flows and damaging our streams. So how would we go about estimating volume of runoff? Let's consider the following equation: R equals P minus L minus G. R is the direct runoff area indicated by the hydrograph, P is precipitation, L is the basin recharge, and G is groundwater accretion, all in units of depth over the entire drainage area. Computation of average precipitation P has been discussed in earlier lessons. So if you go back to the previous videos I've done, you can learn how precipitation P is calculated and the various methods for that. Accurate estimates of R, the direct runoff, therefore depend on estimates of basin recharge L and the groundwater accretion G. In the design storm drains and small water control projects, runoff volume is commonly assumed to be a percentage of the rainfall. If the previous equation is correct, then equations such as R equals K times P may be valid. This equation cannot be rational since the runoff coefficient K must vary with both recharge and precipitation. So the reliability of R equals Kp improves as the percentage of impervious area increases and K approaches unity. So this equation works best when most of the area is a percentage of impervious area, or the larger percentage of the impervious area, the more that this equation applies. Because the more that we have soil that infiltrates and uses vegetation and recharge, as we discussed before, it's going to be much more difficult to keep track in a single event hydrology basis and needs something more like continuous simulation hydrology to be able to measure the runoff appropriately. The percentage or coefficient approach is most suitable for urban drainage problems where the amount of impervious area is large. For moderate rainfalls, all runoff may come from the impervious area, making K the percentage of impervious area. Customary values of K are going to be given in a table in the next slide, and this approach really should be avoided in rural areas with little impervious runoff. You're just not going to get an accurate value at all. So here are some common runoff coefficient K values. So for urban residential, for single houses, it's 0.2. For garden apartments, it's 0.3. For commercial industrial with lots of impervious area, warehouses, parking lots, it's going to be 0.9. For parks, it can vary between 0.05 and 0.3. And then for asphalt or concrete pavement, it's going to be 0.05 to 1.0. In a lot of cases, if you have asphalt, there's just really no infiltration. And so it's going to be much closer to 1.0. So those are a lot of the runoff coefficient K values. Remember that this only really works when there's lots of impervious area. The more that we're in rural areas or places with infiltrating soils, it's just not going to work that appropriately. So I hope this lesson was useful. You can download our free hydrology terms guide in the description down below, and we'll see you guys in the next hydrology lesson.